of N2O5 in the following first order reaction. This is a first order reaction where N2O5 gives NO2 and oxygen. Initial concentration was this much moles per liter at 318 Kelvin. The concentration of N2O5 after 60 minutes was found to be this much. We have to find the rate constant at this temperature. Let's see this reaction. We have this N2O5, it broke into NO2 and half oxygen. At T is equal to 0, the concentration of N2O5 was 1.24 into 10 to the power minus 2 moles per liter M. At T is equal to 60 minutes, the concentration was 0.20 into 10 to the power minus 2 M. The concentration has decreased. And the temperature is given 318 Kelvin. We have to find the rate constant, that is K. Correct. See, the equation we know till now is K is nothing but 2.303 by T log of R naught by R. That is what we know. Correct. So let's find this now. Put the value, this becomes 2.303. Time is 60 minutes. 16 minutes. Log of R naught. Initial concentration is R naught. Final concentration is R. Correct. This gets cancelled. This gets cancelled. This is nothing but, this becomes log of 6.2. Right? This is 2.303 by 60 log of 6.2, and the unit will be per minute. You solve this, you get 0.0304. So that means this is my K. Correct? Just simple application of the formulas. Most of the numericals we will see here, we will just apply the formulas which we have derived. For first order reaction, this is the formula. Please remember, it's a very critical formula. K is nothing but 2.303 by T log of R naught by R, where R naught is the initial concentration, R is the final concentration. Now we'll see the same rate reaction for the first order, but in this case we have the gas phase. Since it will be gas phase, we'll use pressure. And one equation, and let me derive for you. Let's suppose A plus B will give you C, and everything is, or A is equal to B plus C. A gives B plus C. All are in gas. So at T is equal to 0, let's suppose this was P1 atmosphere and these two were at 0. At T is equal to sometime T, this becomes P1 minus X, this becomes X, this becomes X. So P total here becomes what? P1 minus X plus X plus X, right? P1 minus X plus X plus X. And that is nothing but P1 plus X. Here P total is what? P1 plus 0 plus 0. That is Pn. So if you see, the total pressure has increased from P1 to P1 plus X for this reaction. Same formula will apply. We have seen K is nothing but 2.303 by T log of R naught by R. Correct? That's what we have seen. In this case, if you see, R naught is initial concentration of A, that is nothing but pressure P1. R is the final concentration of this, that is P1 minus X. The only trick we will be doing here is, instead of X, we know that X we can write in terms of P total, right? So with this equation, if you see, let this be P dash total or P naught total, initial pressure. So if this is P1 plus X is P total, the final total pressure. So X is nothing but P total final minus P1. With this I can say this is P1 minus X, right? I can say this is nothing but log of P1 by, instead of P1 minus X, I can say P1 minus this value, P total minus P. Correct? So with this I get 2.303 by T log of P1 by 2P1 minus P. Correct? Please don't, this is not any formula which we are deriving. This is just concept I am trying to explain. Don't use this formulas for any gas equation. For any gas equation, if you see, you have to derive this. It may be, it has stoichiometric coefficient of 2 or 3. In that case, it will change. This is just a concept. The concept we are trying to derive here is, we are still using the same formula here, right, which we have seen for first order equation to find the value of K. But instead of initial concentration in moles per liter, we are using in pressure. And instead of using P1 minus X, X is something which we will derive. And this will vary based on the equation. If it has some stoichiometric coefficients, this equation will vary. So X we will derive, and we'll try to find the value of X in terms of total final pressure. Because in generally in questions, they'll be giving us total final pressure, and we'll get this kind of equations. So let's see one numerical on the concept we just explained. The following data were obtained during the first order thermal decomposition of N2O5 at the constant volume, and we have to find the rate constant. If you see, the total pressure is given. So if you see at T is equal to 0, total pressure was 0.5 by T, and total pressure will be because of N2O5 only, because this was 0. So this was 0.5 atm. At T is equal to 100, this will be in seconds. Please note, take care of units, they are very critical. This will be, let's suppose, 0.5 minus 2x, because there is a stoichiometric coefficient of 2. If 2x moles of N2O5 is used, then 2x mole of N2O4 will be created, and x moles of oxygen will be created. Correct? This is 2, this is 2, and this is 1. So this is 2x, this is 2x, this is x. So at T is equal to 100, pressure total is given to us, and that is nothing but 0.5 minus 2x plus pressure due to N2O4, that is 2x, plus pressure due to oxygen. To solve this, this is nothing but 0.5 plus x, and that value is given 0.512. With this, if you find the value of x is nothing but 0.012. Correct? Now we'll use the same formula. K is nothing but 2.303 by T log of initial concentration of N2O5, that is nothing but P naught of N2O5. It is nothing but initial concentration of N2O5. And then final concentration of N2O5 is nothing but pressure of N2O5. Correct? This is initial and this is final. Generally we use R naught by R. Here I am using P naught by P, just to be more explicit. Right? This is nothing but at T is equal to 0, and this is nothing but at T is equal to my 100 seconds. Let's put the values here. This becomes 2.30 by 3 by T is 100 seconds log of P naught of N2O5 we see is nothing but 0.5 atm, and this is nothing but 0.5 minus 2x, and x is nothing but 0.012, that is 0.5 minus 2 into x. X is nothing but 0.012. This much atm. atm cancel. Right? This becomes 0.476. So 0.5 by 0.476 log, and this value, if you actually solve it, this comes out to be 4.98 into 10 to the power minus 4 per second, and that is the value of my rate constant for this equation. Correct? The same concept here. So we have this, use this x, and then since total pressure was given, please note here total pressure is given. If in the question they give the pressure of N25 itself, then it is very easy. But generally, when you are having the reaction is taking place, it is difficult to find a partial pressure. It's very easy to find the total pressure of the whole container where the reaction is taking place. So generally the data is in terms of total pressure. The question says a reaction is first order in A, second order in B. That means a rate is nothing but K, first order in A to the power 1, second order in B, that is B to the power T. The question is first find differential rate equation. So what we wrote is just a rate equation. We'll write differential rate equation. So instead of rate, I'll write minus of dr by dt, minus of dr by dt, and that is nothing but the same value k a to the power 1 b to the power 2. That is my differential rate equation. Correct. The next question is how is rate affected on increasing the concentration of B by 3 times. So let's suppose initial concentration of B was X and I made it 3X. So let's see this. Directly I can say if you make it 3X and this is X square, right? So it will become 3X to the power 2, that is 9X square. That means it becomes 9 times. Just by looking at the equation I can tell that I have to solve it. So let me solve this now for you. So when the concentration is X, my rate, I'll just use this normal thing, rate R1 is nothing but K, concentration of A is A and B is X square. Rate 2, second case is nothing but K, A concentration is same and B becomes 3X square. This is nothing but 9 into K, A square, X square. And this value whole thing is nothing but rate 1. Correct? This value. This becomes 9 into rate 1. So if you see, rate 2 is nothing but 9 times rate 1. That means the reaction has become 9 times. Now the next question is, how is the rate affected when the concentration of both A and B are doubled? So let's do the same thing. Let's suppose the rate 1 is K, concentration of A, let's suppose, becomes Y to 2Y and B Z to 2Z. Let's do this. So initial rate will be A is Y to the power 1, Y to the power 1, and X concentration of B we took Z to the power 2. The final rate rate 3, make it, or rate 1, rate 2 we took, so let's take rate 3 and rate 4. Right? Just to avoid confusion. This K, Y becomes 2Y and Z becomes 2Z. So solve this, this is nothing but 2 into, this is 4. 2 into 4 is 8. 8 into K into Y into Z square. And this whole thing is nothing but, if you see, rate 3. So if you see, from this, rate 4 is nothing but 8 times rate 3. That means the reaction has become 8 times. Pretty easy. You can just assume the initial concentration of the reactant which is going to be changed is X, and the final concentration to be 3X, 4X, 5X, depending on the question. It is if the concentration has become 3 times or 4 times, and then you can find